welcome back to our channel, and in this video we will be looking at benzene. Alright, and remember to like, share, comment, subscribe and all that. Alright, so benzene, alright, formula for benzene is C6H6. Alright, and this is the structure for benzene. So before we get into any naming of benzene compounds or reactions, we are going to observe the structure of benzene. So these are the hydrogens, right? And the black ones are the carbons. So 6 carbons, 6 hydrogen. Now there are 3 terms. We're now going to look at the structure for benzene. There are 3 words that you must be familiar with. So delocalized, conjugated, and resonance. Alright? Alright, so benzene, it is a system, right? It's a ring compound, right? It has delocalized electrons, it is conjugated, and the resonance also exists. So I will explain these terms shortly. Alright, so if you look at the structure for benzene, alright, if you notice it has alternate, double, and single bonds. So double bond, single bond, double bond, single bond, double bond, single bond. Whenever you have a molecule and you have alternate, double, and single bonds, it is said to be conjugated. So conjugated means alternate, double, and single bonds. Alright, now we know that a double bond consists of a sigma bond and a pi bond, right? And pi bonds are found from the overlap of p orbitals. So everywhere you have the double bond, those are formed from the overlap of p orbitals. Now, when you look at this structure, it is showing you that the double bond are in specific locations. So it's here, here, and here. However, this is just a representation, right? So the double bond could actually be everywhere of the single bonds. The double bond could have been there as well, right? So the pi bonds, right, which are made from the overlap of the p orbitals, those contain the electrons, but the electrons in your p orbitals, right, they are delocalized. Once you hear delocalized, you must know that it means they are mobile. Just like the metallic bonds, cations surrounded by a sea of mobile electrons. So here, let me get a hydrogen. Right, so on the molecule, it is showing that the double bonds are in specific positions, right? But those p orbitals that overlap to form the pi bond, the electrons are not in any fixed position as is shown here. They are actually delocalized. So the pi electrons of benzene, they are delocalized. So benzene has delocalized pi electrons. right? So it has alternate double and single bonds, and the pi electrons are delocalized. Now, when you have a molecule, right, with delocalized electrons, then you can have a structure in which those delocalized electrons to represent it, like how I've done here, where double bonds are in specific positions, then you can have more than one representation of the structure, right? So whenever you have delocalized electrons, so these are delocalized, but we put them in specific positions, right? So it could look like this, or I could do a next one where the double bonds are in the other positions. So when I have more than one structure being represented, that is where the resonance comes in, alright? So benzene has more than one resonance structure. So the electrons are delocalized, they are not in any fixed position, but when we draw benzene, there are certain structures that are put forward to represent benzene, right? So those are called resonance structures. The electrons, and that's because the pi electrons are delocalized, they are not in any fixed position. But when you draw a structure for benzene, these double bond has to be in a particular position. So we're going to draw the resonance structures for benzene. Alright, so these now, number 1 and 2, these are the resonance structures of benzene. So remember, the resonance would have come about when you have a molecule with delocalized electrons, right? And you have to draw a particular diagram. So remember, we have 3 pi bonds in benzene. So in the first diagram, I put them, let's number the carbons. This is carbon 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So in diagram 1, the double bonds are between carbon 1 and carbon 2, 3, 4, 5, and 6. In the second one, it's between carbons 2 and 3, 4, 5, and between 1 and 6. Alright? Now, none of these structures are the correct representation of benzene. Remember, the electrons are delocalized, right? So these two are saying that the double bond could have been here, here, and here. The other form of that would be to put them in the other places where you had the single bond. Now, we will have a resonance hybrid, right? So none of these two resonance structures are completely correct, all right? So the resonance hybrid now would represent what, like a sort of intermediate of these two structures, all right? So for benzene, when you look in the textbook and you see this, you see benzene with a circle inside of it. So the circle is showing the localization of the electrons. If you look on the outside, they are all single bonds. You don't have any double bond in place in the hybrid structure. Now the dotted line are a full, complete circle with solid line. This is showing that the electrons are delocalized and not in any position. And this will become important for the reactions of benzene. So, in terms of the structure of benzene, it is a system of what? Delocalized pi electrons. The pi electrons, right? They are not between any specific carbon atom. They are distributed among the 6 carbon atoms, right? It is resonance. Resonance occurs in benzene. So these two are the structures you will be using when you are doing reactions of benzene. And it is conjugated because when you look at these structures, they consist of alternate double and single bonds. Right? Now, when we go into the reactions of benzene now, once you spot the double bond, you will think that benzene is going to react like alkenes because of the double bond. So you would expect it to do addition, but it actually does substitution. Alright? And the reason for that, the benzene ring, when it's like this, it contains the 3 pi bonds, it is more stable. Right? Now if you pursue chemistry beyond this level, you will go further into the stability of benzene. But for this level, we won't go into the stability of benzene. Right? But know that this structure is stable. However, if one of the double bond is broken, benzene will lose its stability. So benzene wants to remain stable, and it is most stable when it has its system of 3 pi electrons. Alright? So what will actually happen is that it will replace one of the hydrogen with whatever electrophile is being added. Because remember, it couldn't have, you cannot add a nucleophile because the benzene ring, it has what? Pi electrons. So that makes it a nucleophile. Anything with a lone pair is a nucleophile. Right? Now, back to join benzene, you will not actually be joining these structures. Right? As in, you won't be joining out carbon and hydrogen. I join like this so that you can see everything. So the 6 carbons with the double bonds and the 6 hydrogens. So I'm going to replace these now with the actual diagrams that you will draw. So these now are the structure for benzene that you will be drawing, right? Without showing the carbon and the hydrogens. So these are the, when you're doing mechanisms, these you can use either of these structures. And this is the resonance hybrid. So the benzene ring with the circle inside showing that the electrons are delocalized. So what will happen now in terms of the reaction when benzene reacts? So now you have to remember that a hydrogen is here. So when you have benzene, right? Remember we said when benzene is like this, it is stable. Alright? Now if you are going to add an electrophile, we know that one of the pi bonds have to break. So if we add an electrophile, right? Let's put E for electrophile. So we know that the double bond would act as the nucleophile, right? To donate the 2 electrons to get the electrophile. So every nucleophilic attack, you're forming a dative covalent bond. So this double bond would have to break to get the electrophile. So as you can see now, the double bond is broken, so benzene is not as stable as it was before. So to regain its stability, the benzene will take back the 2 electrons from this carbon to hydrogen bond and put it back inside of the ring to give the double bond. Of course, you will have a reagent. When we look at the mechanism, you will have a reagent to take this hydrogen. Alright, so the point is benzene always wants to remain stable. Alright, so even when it adds something to the ring, it wants to keep the pi system intact, the delocalized pi system intact. and for that reason it cannot do addition, it will do substitution. Alright? So in terms of reaction, benzene does not react like your alkene because it wants to remain stable. And so when we look at the reactions, you will see that it reacts by substitution. Alright, so the final thing we're going to look at for this part of benzene is what happens when it actually reacts with an electrophile. So we know that, let's say this bond will break, right? Now bear in mind again that a hydrogen is at each position. So if we add an electrophile, right, this carbon here only has 1, 2, and the bond with hydrogen, that's 3 bonds, right? So we know that this carbon here is going to develop a positive charge. Now, positive charge on the benzene ring means that it is not as stable as it was. Benzene is going to try and get rid of the positive charge. Alright? So what will happen now is that the double bond that is here, so first let's look at the structure. Alright? This double bond is going to move up. Alright? So the double bond that is here will move to here. Now if that happens, so let's put the double bond there. Let's put this there. Alright? H. Alright? And this here. Now if you do that, you will know that this carbon now is forming 4 bonds. 2, 3, and the one with hydrogen, that makes 4. But if we check this carbon here, it is forming 1, 2, plus the bond with hydrogen, that is 3. So a carbon with 3 bonds, that is going to have a positive charge. So in trying to get rid of the positive charge from this carbon atom, the double bond, the pi electrons from this double bond moves up. As a result, the carbon here gets a positive charge. And so benzene, the pi electrons here are going to move over to get rid of this positive charge. So double bond is here. This one, it moved over, so it should be here. Alright? And so this part now will get the positive charge. So what is happening here now is the benzene ring is trying to stabilize itself. So we get more than one structures as the intermediate. So once an electrophile is added to benzene ring, the benzene ring is going to get a positive charge, and so the electrons will be moving around in the ring trying to get rid of the positive charge. So this ion formed here, we call it the uranium ion, right? And as we know now, this positive charge, it will not get rid of it until the hydrogen is removed, right? So let's go back here. So this is an intermediate stage when benzene does any reaction. Once it gets the electrophile, alright, this is what happens. The double bond tries to quenches the positive charge. And as I had shown you earlier, right, 2 electrons are in every bond. So this bond, the electrons are going to return into the ring. And when it returns into the ring, that is when the benzene ring is established again. Alright, so this intermediate here is called the uranium ion. And that's what will happen when benzene reacts, because remember, benzene wants to maintain its stability. And that only happens when it has its 3 pi bonds present, right? It's the localized system of pi electrons. Once it loses one of the bonds, it loses its stability. One of the double bond, that is, alright? And so benzene always wants to remain stable, so it does not react like your alkene. We know that when an alkene reacts, right, and you break that double bond, it will be converted to an alkane, right? No, benzene does not want that. It wants to remain as benzene, right? So it does substitution and not addition like the alkene. And for that, when you're going to do certain reactions of benzene, like halogenation, right, or nitration, it will not do it by addition, it will do it by substitution. Alright, so that's it for this part of benzene, just talking about the structure and why it does addition, substitution, reaction, and not addition. So in the next video we will look at naming benzene compounds, and the next one we will do the mechanisms for CAPE. Alright, so that's it for this video.